Hello, I have defined some basic notation, and we consider the linear regression as an example. And let's make it super general. You can think about two different principles of estimation. So first, we are going to assume that theta hat is identified. It is without identification, you cannot do anything with the data. So identification, suppose identification is not a problem. Then there are two different ways to present the identification result. One is to show that theta 0, the true value of theta, maximizes some function. Or you may think it as a minimization, because if you simply take minus of the function, maximization becomes minimization. So maximum or minimum does not matter, and we are going to call both as optimization. So when I say optimization problem, that means minimization problem or maximization problem. So basically the same thing. So anyhow, your identification, sometimes the identification result can be stated as in this way, to say that there is a maximization problem which has a unique solution, and that is the true value of theta. If you can prove that the solution is unique and existence of the solution, then it is an identification result. In this case, the function that is minimized or maximized is referred to as the criterion function. It is the criterion function. It may have different names, but I'm going to call that criterion function. And the second approach is, so the identification result can be stated as that theta 0 satisfies this equation, and this equation has a unique solution. Then the solution is the unique solution is the true value. In this case, I'm going to call psi 0 as the estimating equation. Also, it does not have good name. By the way, I'm combining results from different papers and different textbooks. So criterion function is commonly used, but estimating equation is not a common name. I could not find any better name. I'll just call this the estimating equation. For example, from the earlier example, so this is the identifying equation, estimating equation. So beta 0 is identified because this equation has a unique solution for beta. Then that's identification. Or you may state the identification condition as, say, we have this minimization problem, and this minimization problem has a unique solution, and that is the true value of beta. That's another way to present the identification condition. If you can prove the uniqueness of the solution, and then they correspond to one of them. Usually, you may choose how you present, whether to use the optimization, the criterion function or estimating equation. It's not. They may be interchangeable sometimes. And then, from each approach, from each type, you have one type of estimator. You can get different types of estimators from two different ways to present the identification. The first one is M estimation or extremum estimation. So M estimation means like minimization or maximization. I don't know if this M stands for minimization or maximization, but coming from there. And statisticians call this M estimation, but econometricians call this extremum estimation. Same thing. They are the same thing. And the idea is the same. We know that theta is identified as the unique solution to a maximization problem of a certain criterion function. And then what we need to do here is we are going to estimate the criterion function using the sample data, and say estimator for the criterion function is Q hat. And then what you do here is solve the maximization problem using the estimator for the function. So theta hat solves the maximization of Q hat, right? Intuitive. So you have seen the exact same framework from the least squares estimator. Least squares is this one. So go back here. So we know that beta is identified as the unique minimizer of this population mean of squared errors, but the population mean of squared error is not observed. It is not available. So we estimate the population mean as the sample mean of squared residuals, and minimize the sample squared residuals. That is the OLS estimator. That's an example of extremum estimation, and maximum likelihood is the same. It also maximizes something. So minimization, maximization are the same. So these two examples, famous examples, fall into the case of extremum estimation. So extremum estimation is more common in many cases in econometrics. And an alternative is Z estimation. I think the name Z is coming from 0. So it makes something equal to 0. I guess, I don't know if that is right, but I understood the name that way. So Z estimation makes the equation, estimating equation to 0. So we know that the identified theta is identified as the unique solution to psi equals to 0. And then what we do here is estimate psi using the data and solve it. Solve this equation, solve this equality. Then the solution from the data is your estimator. Or in some cases, there may not be an exact solution to 0. And then you may choose something that you may choose a value that is closest to 0 as possible. So anyhow, find a solution or reasonable solutions to this equation. The most famous example in this case is the generalized method of moments. Method moment is what statisticians developed, but it is generalized by econometricians to GMM, generalized method of moments. And we are going to study this estimator in the next chapter separately. And it's so important, and so we are going to spend a lot of time on GMM. And you are going to use GMM in your dissertation. I'm pretty certain it's a very popular and widely used estimator. Okay, so it's just conceptual division. I just want you to give you the intuition, the basic principles, but in practice it's not that important. And also what's interesting here is, as I said, in most cases you may choose whether you use M estimation or Z estimation. You can use this like either one, and the results may be in many cases are equivalent. So it is not a big problem. You cannot say one is better than the other. Just one may be more convenient to compute or to derive the properties in analysis. So like for example, you may think about M estimation, which is maximization. Then how can you solve that? We usually assume that the second order condition is satisfied, and then we find the first order condition and solve the first order condition. Then the first order condition is a Z estimation, right? So first order condition is written this way. This is a Z estimation, and alternatively, Z estimation makes something equals to 0, but making something equals to 0 is actually very difficult to solve like on program. Numerically, it's really hard. So what you do here is you simply, like for example, take square of this and minimize that, like least squares. Least squares want to make epsilon as close to 0 as possible, so minimize its square. You may, like later, redo pretty much the same thing from here. Based on this, we are going to minimize square of this estimating equation. Then minimizing a square is M estimation. So in that sense, M estimation and Z estimation are mixed up in some cases, and it helps you to understand, to see what is underlying framework of an estimator. That is why I'm introducing you those concepts. Okay, I will stop here, and so in the next video I will teach you something more practical and more useful.